enjoyed by maybe the more math geeky type of students. We'll go through some theoretical aspects. Also, we'll go through some proofs. Okay, it's a very nice proof, so I hope you can appreciate it towards the end. But we still have one little piece we need to finish. So last time we talked about Newton's divided difference. We have an algorithm to compute all those coefficients, and then once you have the coefficients, you have this Newton's polynomial, right? So we'll start from there, and what's going on? So introduce you to something called the nested form. Okay. So from last time, we know once we have the coefficients and we have the data, we can have this Newton's polynomial. It takes this form. Let's write it out. So we write it out as the way we derived it. So have A0, the first term, and then I improve it into a polynomial of degree 1. I put in my A1, right? And then I put in my A2. It's multiplied by that. Now it's polynomial of degree 3. Let me take one more turn. Dot, dot, dot. There are many. And then to the last one. That's an. All these multiplies. It's a product of all these terms. All right. So once you have found all these AIs and then you have all these x's, so you have the polynomial, you know it can be written like that. So now I say, can you plot this polynomial for me? Or I give you any x, can you tell me the value of this polynomial? Then you have to code this expression in the computer, say, give it to MATLAB, right? So how do you code it? And I'm interested in the computational intensity, meaning how much work it is for the computer to evaluate this expression. Okay. So in computer science, these operations, each of these basic arithmetic operation, the time it takes in the computer, it's called a flop. So we're going to count how many flops. Right? Flop is one computation needed. So how many flops? Number of flops equals to what? So let's go through. So the first one, you don't need to do anything, but you need to add it on the top. So there is a plus going on. So one flop is enough. And let's say now I want to add the second one. How many flops do I need? 1, 2, and then I need to add on top, right? So let's say 3. And then if I want to evaluate this, I need 1, 2, and 3, and 4, and then I need to add it on top. Is that right? So about 5. And how many flops do I need here? Well, 1, 2, 3, and then 4, 5, 6 multiplications, and then add on top 7. It looks like it's like something like 2n minus 1, or 2n plus 1. Do we agree? Each time it gets bigger by 2n. So something like 2n plus 1 plus 1. Yeah. Because n is 0 there. So what's the sum of something like that? Any of us quick? I just want approximately. So isn't this the area of a triangle? Isn't it? That's how I memorize it. 1 here, 3 here, 5 here, 7 here. So how many dots is a triangle? It's about n here, is about 2n. Okay, throw away the 1, doesn't matter, right? So what's about this area? N squared. Do you agree? Approximately. Maybe some small arrows on and off. It's about n squared. Well, that's a lot of work. I think I can improve on that because look at the expression here. X minus x0 appears here. And it appears here. and it appears here, and it appears here. Why do I do it n times? Right? I'm doing it n times in this expression. Do you see? I could take advantages of the structure of this polynomial and write it into the following form, and this is the nested form. Okay, so I do the following. I take out a0, so a0 is out, and I look at the rest. All the terms remaining, there is a common factor shared by each term. Do we spot it? What's a common factor? A hint, it's underlined. X minus x0, do we see that? I take that out. And then this term becomes a1, right? Plus. So I have taken care of the first term and the second term. So the first term I took care of, and these factors I took out, and then now I took care of the second term. Bless you. So what do I have now from the remaining, from the third term and so on? Does it have a common factor, all of them? What would that be? X minus x1. Right? I take that out. So I took this out, I took this out, and I took this one out. And then I put a2 plus. So I took care of this term, right? And you see I can keep going. Is that right? Do you see this nested shape? That it just goes deeper layer and deeper and deeper layer. So all the way until the last term that you get a n minus 1. Once you take that out, then you have only a n, and then you get one term, x minus x n minus 1. How many? 1, 2, 3, 1, 2, 3. I need one more. Okay. Is that okay? So I'm going to erase that. Okay, so this is the nested form, and you can code this in a computer very, very efficiently. So you see now, in order to code this, I would have to throw in a double for loop. I need one for loop going through each a0, a1, a2, so I from 0 to n. And then in the loop, I need to go through from 0 to I, right? So 0 to 1 for this guy, 0, nothing here, 0 to 1 here, 0 to 2 here to do this multiplication. But in the nested form, you see one for loop is enough. I could start from this one, I evaluate this value, and then I go a for loop. Each time I multiply by this and add that. I multiply by this and add that, and just keep going. Okay? So let's write out this algorithm. So it's not any code, it's called a pseudocode. Pseudocode means just the algorithm is being listed here, and then you have to adapt it to the syntax of your programming language. Okay? So pseudocode takes the following form. So let's say I have the following, given now a0, a1, an, all those a's, and then x0, x1, xn, and then I also need to have an x. So I'll be evaluating Pn at x with this code. Okay? So I do the following. So for my code, the step 1, so the P. Okay, so I set P equals to an. I set P to be this guy first, and then I have a loop, for loop. Let's say my index is k from n minus 1, n minus 2. It keeps reducing all the way to 0. Okay. And then in each step, what do I do? So this n, at that k equal to n level, what do I need to do is it has to be multiplied by this guy and then add on this guy on top. Then that's my next level. Okay, then I can keep going, right? So I modify the p value with the following. I take p, multiply xk, is n minus 1 here, and then I add on top the ak. Then I get this value, right? And then I can keep going. And is that okay? Now, call your attention. I use index running from 0 to n for this pseudocode. In MATLAB, it doesn't take 0 as an index. I know some programming languages, they do, but MATLAB, it has to run from 1 to n plus 1, and you have to adjust it a little bit. Be careful, all right? Usually that's what happens to me, that my code doesn't work just because I messed up the index. So be careful, it's easy to mess up with the index. Okay, so let's count now. How many flops do I need to do this computation? So this for loop, what is the length of this for loop? N, is that right? Inside each loop, what do I need to do? 1 flop, 2 flop, and 3 flops. Is that right? So the total flops would be 3 times n. Okay, it's much better, right? Is it clear? Are we okay? Okay, so that's programming part. Now we need to talk a little bit about theoretical aspect. So we have looked at 3 different methods of finding interpolation polynomials: the van der Waals matrix, and then the Lagrange form, and then now the Newton's form, right? And we have seen them being applied to different examples. So along the way, I have been hinted to you. Look, we get the same matrix for the same problem with a different method. So now we're going to talk about this theoretical aspect, and that is, if I give you a problem like this, does it exist always some polynomial that will do the interpolating job? If it does, how many are they? Is there only one, or can I find multiple of them? Okay, so that is the existence and uniqueness. Of polynomial interpolation. Okay, I'll stop here. Okay, so in order to do that, I need to borrow some theorem, which we probably know. If not, I'll repeat it here. Some fundamental theorem of algebra regarding polynomial. Okay, so I'll state it. So if I have a polynomial, this is all about polynomial. So I say every polynomial Pn, that is a polynomial of degree n, okay? Pn of x is not identically equal to 0. Is it okay, this shorthand? If I write 3 lines, that means identically equal to 0, then the whole function is just constant 0. If I put a line on it, that means at least for some values of x, the function is not 0. Okay? So it's not an identically 0 function. Okay? And then every polynomial like that has at most n roots. Okay, so when I'm talking about n roots, I'm counting multiplicity. Meaning, if it's a double root, it's counted twice. If it's a triple root, it's counted 3 times. Okay, so the root could be real or complex. It doesn't matter, we count them. Okay? So as a consequence of this theorem, this implies immediately the following. Let's write it out. Now, if I shall have a polynomial Pn of x, if the polynomial has more than n roots, what happens to the polynomial? The polynomial is of degree n, and then I found n plus 1 roots. For n plus 1 different values of x, the polynomial equals to 0. What is the polynomial? It has to be identically equal to 0. Is that right? Then you have infinitely many roots. Is it okay? We understand this argument? Because that's the backbone of our uniqueness theorem. Once you have this, it's very quick to prove. Okay, so let me give you the basic theorem. this theorem here, existence and uniqueness. Okay, let's set it up. Okay, so if I say, given a data set, xi, yi, I from 0 to n plus 1 data set, I have to be careful. I have to say all these xi's are distinct, otherwise it doesn't work. Okay, then there exists one and only there's only one polynomial Pn of x of degree n such that Pn interpolates the data, meaning Pn evaluated xi equals to yi for I from 0, 1 to n. Okay. So the theorem actually says two parts. One part is existence. It says for this interpolation problem there exists a solution. And the second part says there exists only one. Okay, so existence and uniqueness. Okay, so let's go through a little proof for that. It's a very short proof. So let's start with the existence. Do we need to worry about the existence? What do you think? Have we already shown it? What do you say? Yeah. Does it always exist, such a polynomial? Come on, we have 3 ways of constructing it, don't we? Throw in the Lagrange form, you can write it out. That one works. Or Newton, or the Van der Waals matrix. Is that right? So by construction, I know that it always exists, no worry, okay? By construction, so no proof. I already know I have 3 methods that I can construct these polynomials. So the thing needs to be proved here is the uniqueness. How do you show that no matter which method I use, I always end up with the same polynomial? Always the same. Okay. So if you want to show there exists only one solution, what argument can you think of? Any suggestions? What argument? I want to show there is only one solution. Any ideas?
At every xi, Pn is always equal to yi for all 3 methods.
What if I have a 4th method? I want a general argument.
To prove that for all methods, it seems like a circular argument to me. But
You want to show with all 3 methods you end up with the same polynomial? How about let's assume by some method and then some other method I managed to find 2 polynomials. Then I show they have to be the same. Then I'm done. I'm not specifying a particular method. Assuming there exists one solution and another solution, and then I show that they are the same. Is that okay? It's kind of a contradiction. You can see, assume they are different, and then you show they have to be the same, so it contradicts. So there is only one, right? So let's see, let's follow that. So assume there are 2 such polynomials. Okay, that will do this interpolating work. So they are of degree less than or equal to n. So let's call it P of x and Q of x. So these are polynomials. This fancy P means the set of function with all polynomials of degree n. Okay, the polynomial of degree n such that they both interpolate. So P xi equals to yi and Q xi equals to yi for all these I from 0, 1, and n. Is that okay? So they do that, and then I form a new function. Let's say, let's call it g of x, just to be the distance between these two, px minus q of x. If by some argument I can show this g has to be identically 0, I'm done. Agree? Agree? Identically equal to 0. Hint, 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 why I put that fundamental theory of algebra there. I'm going to use it. That's my main argument there. Okay, so which means I need to find zeros for this g, don't I? So what are zeros for the g? Let's check. G of xi, for any of these I, what do I get?
0.
0. Is it obvious? Because this is yi and this is yi. This is 0, right? So this holds for I from 0, 1, all the way to n. So how many zeros do I have now? N plus 1 zeros, isn't it? And now pay attention, g is a polynomial of degree n minus a polynomial of degree n. So g is himself a polynomial of degree n. Agree? And it has n plus 1 zeros. What can it be? By that theorem, g of x must be identically equal to 0. Okay, then you're done. Then p must equal to q, and they are the same function. Identically equals to q. Therefore, there's only one. Is it okay? Can we buy this argument? Well, of course, you have to accept the fundamental theorem of algebra. Assuming that is correct, I can use that to show the uniqueness. Okay? All right, any questions? Okay, so now we know that there always exists one and only interpolation polynomials. And now I worry about something else. Always, I want to talk about arrows. Okay, so all numerical methods are approximations, and in the end, the arrow analysis becomes crucial, right? You need to know, what does it depend on? How big is it? How can I improve and to get smaller arrows? It's all about arrow analysis. Okay, so I'll give you this big theorem, and then we'll attempt to prove it. So each time you state a theorem, you have to be careful. You have to state it clearly under what assumption does it apply and how does it apply. Okay, so I'm going to set it up. Okay, so I have a function fx. Okay, smooth, let's just say smooth, can be differentiated many times. And then it's defined on the interval from a to b. Okay, and then I also have a set of data points xi, distinct, I from 0 to n. This is on the interval from a to b as well, and distinct. Okay, and the distinct. And then I have a polynomial of degree n that interpolates my function exactly at those data points. Okay, so Pn is a polynomial of degree n, and it interpolates. Satisfy the following. So what does it mean? I have, I can write it here, f at xi equals to Pn at xi for all these i's, n plus 1 points. Okay? And then define the arrow. Actually, the arrow function here, I'm just looking at a function. So e to the e of x equals to just the distance between them. Okay, So f is defined on the interval from a to b. Polynomial is defined for any x. Then this function is defined on the interval from a to b. Agree? Okay? Okay, and then I have the following theorem that tells me exactly how big the arrow is. So it says there exists a some value psi on the interval from a to b, I don't know exactly where, such that the following holds: the arrow exactly equal to 1 over n plus 1 factorial f to the n plus 1 derivative evaluated at psi times the product I from 0 to n x minus xi. Okay? And this holds for all x on the interval a to b. So I want to point out that this is actually a very strong statement. It's not even an estimate. It tells you the arrow exactly equals to that, right? I'm not saying it's bounded by something. I can put a big stuff there. This equals to. And the second, look at the right-hand side, the expression for this arrow. It does resemble a little bit the arrow for the Taylor series, doesn't it? For the Taylor series, I have this guy, I have that guy, but over here is x minus c to the power n plus 1. So instead of x minus c n plus 1 times, I have x minus all the interpolation points. Okay, so it's very similar. So let me block this, and hopefully we could memorize this form. Is that okay? That's important. So I plan to go through the proof. It takes a little time, but it's such a nice proof. So I want to show it to you. Is it okay? Are we okay going through a proof? And many other theorems I'll throw at you without proof. But let's prove this one. Okay? So let's try proving it. Okay, so I start the proof with looking at a couple of trivial situations where this estimate holds, obviously, and then I don't have to do anything. So let's say, what is the first trivial case? Let's say if my function f shall be a fancy p, that's a polynomial of degree n, is there anything I need to do? If I'm interpolating a polynomial of degree n by a polynomial of degree n, what do I get? We just talked about uniqueness. By uniqueness, your Pn will exactly equal to f, isn't it? Because there exists only one polynomial that will do the job. Agree? By uniqueness, what do we have? We have fn shall identically equal to pn, right? And then the arrow is identically 0, and then there's nothing to show. You get 0 equal to 0. The right-hand side is 0. It's trivial. Okay, so we not consider that, and now we consider, let f be not a polynomial of degree n. That means if you differentiate it n plus 1 times, it's not 0. There's something still there. Okay? Okay, and let's consider another situation that is trivial. That is, if I'm looking at this arrow formula where x shall exactly equal to one of the interpolating points. So if x equals to xi for some I, is there anything I need to do? Well, then the arrow is 0, isn't it? And then the right-hand side, I will have x I matches one of these, that will be 0. It's trivial. You have 0 equal to 0. Do we see? Are we okay? EXI equals to 0, and it's trivial also. Okay, so I am not going to consider that. So now I'm considering the case where f is not a polynomial and x does not equal to xi for any I. Okay, I'm considering x that's not a point that you interpolate, meaning you actually have some error. Okay, so I need to define a couple of things. Okay, so let's say first I define, just say let. I'll define a few things. Okay, I will call a function w. So I will take this product thingy here and then call this w of x. That's what I basically will do. So w x minus xi is this product. Is that okay? I just call that thing w. So what's special about this w? What do we know? W at xi for any I, what will that be?
0.
It will be 0 because it will, one term will be 0. Is that right? For any I. Okay. And what about if I differentiate this w on n plus 1 times, what do I get? Any suggestion? So what is this w? Is this a polynomial? Of what degree? What's the highest power? How many terms am I multiplying? N plus 1. Is that right? So this one actually equals to x to the power n plus 1 plus lower powers of x. Do we agree? If I differentiate this n plus 1 times, what do I get?
Constant.
What is that constant? Be very specific. So all the lower power of x terms, you differentiate n plus 1 times, what happened to them? 0. So what happens when you differentiate this n plus 1 times? You get n plus 1 times n minus 1 times n minus 2 times all the way down to 1. Is that right? So you agree with me? It's n plus 1 factorial, right? So we're getting this factor here, n plus 1 factorial. It will go there. Okay. Okay, I need to define something else. Okay, so now I fix a parameter, we call it y. It's a parameter, so for the rest this is fixed. And then y does not equal to xi for any I. Okay, and then I define a constant. It's c, I call it c, it's a constant. Right now y is fixed. So it's f of y minus Pn of y over w of y. Okay? So for a fixed y, this is a fixed number. Okay? And then I also have a new function. This is a crucial function here. So phi of x is defined as fx minus Pn of x minus c times w of x. Okay? So this is a function of x, right? I am interested in the number of zeros of this function that I just defined. So let's check number of zeros for phi of x. How many zeros can I find? If I evaluate phi at xi, which is an interpolating point, what do I get? Let's put in the expression f of xi minus Pn of xi minus c times w at xi. Did someone say 0? Why is it 0? Do we all see it's 0? Because the first two terms exactly equal to each other, so they subtract to 0, right? And then w at xi, we just say it's 0 for any xi. Is that right? So that's 0 also, and c is a constant. So this is a 0. So this gives me how many zeros? n plus 1, right? I have n plus 1 such points. So this gives me n plus 1 zeros. Okay, I see there is one more. Don't believe me? I'll show you. There's one more. If I evaluate the phi at this point y, which is fixed for this argument, what do I have? I have f of y minus Pn of y minus c. Let's put the expression for c is fy minus Pn of y over w of y. So this is the c, okay? Times w, and now evaluate it at y. What do I get? Isn't it 0? It's just all gone. This one cancels that, and then this is the same, so they cancel. Do we see that? I find another 0. And now y does not equal to any of the xi, so this is a new 0. All right? So there are n plus 1 here plus an additional 0. So how many number of zeros? How many do I have now? I have n plus 2, isn't it? Okay, so here comes the main argument. Let's hope you agree. Here comes the deduction argument. Okay, so phi of x has n plus 2 zeros on the interval from a to b. Okay, that's what we just discovered. Okay, if a function has that many zeros and I differentiate the function, what happens to the derivative? How many zeros would I have? Guaranteed.
N minus 1.
You lose 1 0. Is that right? Yeah, n plus 1, yeah. You're thinking n plus 2 minus 1. Yeah, so you lose 1 0 each time you differentiate on that interval. Is that clear? And then you differentiate it twice. Well, then you get only n zeros on that interval. So I'll keep differentiating. I'll differentiate all the way to n plus 1 times. How many zeros will I have now? I reduce this n plus 1 times, it becomes 1. Very precious, has 1 0 on that interval. Okay, I know there exists 1 0, even though I don't know exactly where it is. And that is the 0 I'm going to call Kasai. Okay, so I'll call it Kasai. That's the last 0. Okay, so what does it mean? So I have phi n plus 1 at Kasai equals to 0, where Kasai is on the interval from a to b. Is that clear so far, the argument? Okay, we're almost there to close it. So, what is the n plus 1 derivative of my phi? Well, my phi is defined here, so I have to differentiate this n plus 1 times, and this one, and that one. So let me write it out. I'll have f n plus 1 time derivative at Kasai minus Pn n plus 1 times derivative at Kasai minus c times on w n plus 1 times derivative at Kasai. Is that right? I'm just differentiating every term n plus 1 times. Okay, so the first one, nothing to do because I don't really know about this f. It's just a generic function. What about that one? And that's a polynomial of degree n, and you differentiate n plus 1 times, what you get?
0.
0. And What about the last one? Okay, I'm keeping the c here. W n plus 1 times derivative. What do I get? We worked it out somewhere. I remember we did that, right? Is that right? It's n plus 1 factorial. Is that right? And then this shall be 0 for some psi. So what does it mean? This term equals to that term, isn't it? Okay, so let me write it out. So this means f n plus 1 derivative of psi must equal to n plus 1 factorial times c. So let's put back the expression for c. We set it up. So it's f of y minus pn of y over w of y. So that's what we have shown so far. We're almost there. So you see, up to now, until this argument, we have the y fixed. So where did we introduce the y? We introduced here, y is any number that you can choose as long as it does not equal to xi. Otherwise, it's trivial, right? So there is no restriction on where you can choose your y. So at this step, I can let the y be the variable and say that this expression holds for all y that does not equal to any of the xi's. Is that okay? And then y becomes the variable here. I can write it back. So write y as x, and then you get the estimates. So I'm going to keep this on the left. So I have f of x minus pn of x will equal to, I move everything to the other side, so I 1 over n plus 1 factorial times f n plus 1 psi times w of x. And that's what you wanted to prove, because w of x is just that product. Okay? And then this one holds for all x on the interval from a to b. How is that? Any questions? Any comments on this proof? We like it? It's pretty neat, right? Can you come up with a different proof, maybe? Prove the same thing? You wonder, how does anyone figure out a proof like that and begin with introducing all these things? Seems so far-fetched that in the end, exactly fitted into what you wanted to show. Okay, I'll give you one little example before we finish. So I know it's a hard proof to digest. So let's use this theorem and see what we can do. A little example. Okay, I want to rewrite this theorem out in the simplest case, say for a very small value of n. Let's say n equals to 1. Okay? If n equals to 1 and I'm choosing x0 to be a, x1 to be b, and let's say b is bigger than a. And then what I'm doing, I'm interpolating a function f, if you want to have a graph. So I have a function f like that, and you have 2 points, a and b, and you are interpolating through 2 points, which means you're approximating by a linear polynomial, right? And I want to see how big is the arrow, all right, on the interval from a to b. Okay, let's say f is defined only on that interval. Okay, and then for x on the interval from a to b, let's say maybe that's where my function is defined, what do we have for the arrow? So e of x, let's get a bound. So let's look at the absolute value of it. So following my theorem, which we just proved, this is 1 over 2 factorial, so it's 1/2 f n equals to 1. So second derivative for some psi in absolute value. Is that right? I'm taking absolute value everywhere. And then the product will contain 2 terms, x minus a, x minus b. Is that right? So far it's still equal sign. So I want to give something called an arrow bound. Arrow bound. And very often it's also called an upper bound for the arrow, meaning the arrow is different for different values of x. X lies on the interval from a to b. But then I want to have some quantity that will tell me that this arrow is bounded by that quantity, no matter which x I choose. So I want to find something that bounds this expression. So I know for sure the arrow can be maximum this big, right? Okay, these are arrow estimates. Okay, so then I will get something bigger because I want to bound this quantity. So, and half stays there. What happened to this one? That is actually given. Once the function is given, it's given. There's nothing you can do about it. So you could say I could find the maximum value of this f double prime of psi for psi on the interval from a to b. Once f is given, this value is given, right? So it's fixed. And then what remains will be to find the maximum value for this expression for x lies between a and b. How would you do that? I will write it down here. Maximum of this expression, x minus a, x minus b, an absolute value, x between a and b. How do you find the max of that? This is just a parabola, isn't it? It's like that. It has a max. How do you find it? Can't you differentiate this polynomial once and find the 0 and plug it back in? Is it clear? I don't work it out. I'll tell you what that is. That's b minus a squared over 4. Right? You work it out, okay? It's elementary computation. So I can put this up. b minus a squared over 4. So that is the arrow introduced by doing piecewise linear interpolation of a function and the arrow on this interval from a to b. Okay, so it looks like nothing, it's just derived from there. But actually, let me rewrite it, ax. This, in the end, is a very important estimate on its own, right? So in particular, later on, we'll take very small intervals. So b minus a will be h, will be a grid size, and that will tell you the order of the method in the end. Okay. Are we okay? Any comments on the proof? Are we happy that we proved something? Okay, so Friday I'll see you in the lab and we'll go through some